September 1940. RAF Bomber Command Headquarters, High Wycombe. 1 in 4 British bombers isn't coming home from night raids over Germany. The Air Ministry demands one solution: more armor, heavier guns, thicker steel. Geoffrey de Havilland, a 58-year-old aircraft designer, walks into their briefing room with blueprints for the opposite. A bomber with 0 defensive guns, built almost entirely from plywood. Speed is the only armor you need, he tells them. They think he's lost his mind. Metal is scarce, yes, but wood. That's for furniture, not frontline bombers carrying 4,000 pounds of explosives to Berlin. De Havilland calculates his wooden aircraft will fly at 400 miles per hour, 50 miles per hour faster than Germany's frontline Messerschmitt fighters. The math is radical. The stakes are existential. October 1940 loss rates 8.9% per week, mathematically unsustainable. His company's reputation hangs on proving wood can win wars. What the Luftwaffe pilots didn't know as they climbed to intercept Allied bombers in 1942 was that they were about to chase an aircraft built by piano makers and furniture craftsmen, one that would achieve the lowest combat loss rate of any bomber in the war and rewrite every assumption about what wins in the sky. Could an idea made of glue and plywood really outrun the entire German Air Force? If you want more buried stories where the history books left out the details that changed everything, hit that subscribe button. And drop a comment, let me know where you're watching from. I love seeing how far these reach. September 1940. The numbers told a story no amount of courage could rewrite. RAF Bomber Command was bleeding aircraft faster than Britain's factories could replace them. In the first week of October alone, 31 bombers failed to return from night raids over Germany, an 8.9% loss rate that, if sustained, would erase entire squadrons within 3 months. The mathematics were brutal and simple. At this rate, Bomber Command would cease to exist as an effective fighting force before Christmas. Air Chief Marshal Sir Charles Portal stood in the operations room at High Wycombe, watching red pins marking lost aircraft accumulate on the situation map like a plague spreading across occupied Europe. The solution everyone demanded was obvious: more armor plating to protect crews from flak and fighters, more defensive gun turrets to fight back, more metal to build stronger, tougher bombers that could absorb punishment and still bring their crews home. Britain's entire industrial strategy bent toward this logic. Aluminum was the currency of survival. Every ounce rationed, prioritized, fought over by competing ministries. The Spitfire production lines consumed rivers of it. The new 4-engine Lancaster bombers demanded even more. There was never enough metal to meet demand, never enough protection to guarantee a crew's safe return. Into this crisis walked Geoffrey de Havilland. He was 58 years old that autumn. A designer whose career spanned the entire history of military aviation, from the fragile canvas biplanes of 1914 to the sleek metal fighters screaming over Kent during the Battle of Britain. His company, de Havilland Aircraft, had built trainers, fighters, racing planes that set world speed records. He understood aircraft the way a watchmaker understands precision. Every gram of weight measured against every increment of performance. Every design choice a compromise between competing forces. But what he proposed in his meeting at the Air Ministry on a gray morning in late September was no compromise. It was heresy. He unrolled blueprints across the conference table showing an aircraft that violated every principle the war had taught. A twin-engine bomber with no gun turrets, no defensive armament whatsoever, no armor plating protecting the crew. And most shocking of all, a fuselage and wings built almost entirely from wood. Not steel, not aluminum. Plywood, balsa, and Canadian birch bonded with industrial adhesive in techniques borrowed from furniture making. The ministry officials stared at the drawings as if de Havilland had proposed attacking Berlin with paper airplanes. Air Commodore Ralph Sorley spoke first, his voice carrying the exhaustion of a man who had signed condolence letters to too many widows. Wood was for training aircraft, for cheap civilian planes, for desperate measures when nothing else remained. Frontline bombers needed metal, protection, firepower. The Luftwaffe fielded some of the most advanced fighters in the world. Messerschmitt 109s and Focke-Wulf 190s could tear apart any aircraft they caught. How could an unarmed wooden bomber survive what heavily defended Wellingtons and Hamptons could not? De Havilland's answer was a single word: speed. His calculations, verified by wind tunnel tests at the Royal Aircraft Establishment, predicted a top speed exceeding 400 miles per hour, 50 miles per hour faster than any operational German fighter. The bomber would outrun threats rather than outfight them. Wood, he explained, offered advantages the metal advocates ignored. It was lighter, requiring less structural reinforcement. It didn't consume strategic materials needed for fighters and tanks. Britain had forests. Canada had forests. The Empire's timber reserves were effectively unlimited, while aluminum smelters ran at maximum capacity with year-long backlogs. More critically, wood was easier to manufacture. Furniture factories across Britain sat idle or produced training aircraft components. Piano makers, cabinet makers, craftsmen too old for military service or too specialized for infantry could build wooden aircraft using skills they already possessed. No need for specialized metalworking tools, no need for rivet guns or welding equipment, no need for the highly trained workforce that aluminum construction demanded. The officials weren't convinced. Speed was theory. Combat was reality. Bomber that couldn't defend itself was a coffin with wings no matter how fast it flew. And wood? Wood rotted. Wood burned. Wood absorbed moisture and warped. In tropical climates, in monsoon rains, in the temperature extremes from Arctic to desert, wood failed in ways metal never would. De Havilland listened to every objection, his expression unchanging. Then he mentioned his son. Geoffrey de Havilland Jr., 27 years old, was an RAF test pilot flying the same dangerous night missions over Germany that were killing 4 crews out of every 10 sent. The older de Havilland wasn't proposing this aircraft as an experiment or a curiosity. He was proposing it as the machine that would bring his son home alive. That would bring every pilot's son home alive. The room went quiet. Portal, the Air Chief Marshal, studied the blueprints again, his finger tracing the clean lines of the fuselage, the elegant wing design, the twin Rolls-Royce Merlin engines mounted in streamlined nacelles. The same engines that powered Spitfires. If the performance calculations were accurate, if this wooden bomber could really achieve 400 miles per hour, it would be faster than almost anything in the sky. Fast enough to reach Berlin in daylight. Fast enough to photograph targets no reconnaissance aircraft could survive approaching. Fast enough, perhaps, to change the mathematics of loss rates that were destroying Bomber Command one mission at a time. On March 1, 1940, Specification B-140 was issued, a contract authorizing de Havilland to build a prototype. The stakes were absolute. If the aircraft succeeded, it could revolutionize Britain's bombing campaign, provide a tool for precision strikes that heavy bombers couldn't execute, and conserve precious aluminum for the fighters defending British airspace. If it failed, de Havilland's company would be discredited, its resources wasted on a wooden fantasy while the war demanded practical solutions. The timeline was punishing: 12 months from contract signing to combat-ready aircraft. De Havilland's team relocated to Salisbury Hall, a requisitioned 16th-century manor house in Hertfordshire chosen for its isolation and security. There, in workshops that once stored hay and housed carriages, furniture makers and aircraft engineers began building what skeptics called de Havilland's wooden folly and what history would remember as the Mosquito. The clock was running. Germany controlled the skies over Europe, and Britain's survival depended on whether plywood and glue could outperform steel and bullets. January 1941. While Spitfire factories in Southampton and Lancaster assembly lines in Manchester consumed every available ton of aluminum, de Havilland's team at Salisbury Hall was sourcing an entirely different supply chain. Canadian birch arrived in crates from lumber mills in Quebec. Ecuadorian balsa, light as foam but structurally rigid, came by cargo ship through U-boat-infested Atlantic waters. Sheets of plywood, carefully graded for strength and grain consistency, filled warehouses that once stored aristocratic furniture. This was material science operating outside the conventional channels of military procurement, a logistics operation that looked more like preparing for a construction project than building a combat aircraft. But the genius of de Havilland's design lay precisely in that transformation, taking materials the war machine had overlooked and turning them into weapons. The workforce assembled at Salisbury Hall represented an equally unconventional approach to aircraft manufacturing. These weren't the skilled metalworkers who riveted aluminum sheets onto Spitfire frames or welded steel reinforcements into Lancaster fuselages. These were furniture makers, piano builders from London workshops bombed into rubble during the Blitz, cabinet makers from Yorkshire who had spent 40 years crafting dining tables and wardrobes for country estates, joiners and carpenters, many in their 50s and 60s, too old for military service but possessing skills that suddenly made them vital to Britain's war effort. They arrived at the requisitioned manor house uncertain whether their peacetime craftsmanship had any place in modern aerial warfare. What they discovered was that building the Mosquito demanded exactly the precision they had spent lifetimes developing. The fuselage wasn't riveted or welded, it was carved, shaped, and bonded using techniques that would have been familiar to a master furniture maker in the 18th century, now adapted for the speed and violence of 20th century combat. The construction method itself was revolutionary. The fuselage was built in two halves, each formed inside massive wooden molds that gave the plywood its curved aerodynamic shape. Layers of birch plywood, each just 3 millimeters thick, were placed inside the molds with balsa wood sandwiched between them for structural rigidity. Then came the adhesive, a casein-based glue derived from milk protein spread in thin, even coats between each layer. The mold halves were closed, pressure applied, and the assembly left to cure for hours while the glue bonded wood to wood with a strength that rivaled welded metal. When the halves were removed from their molds, they were hollow shells, smooth on the outside, ribbed with internal stringers for support, light enough for 2 men to lift, but strong enough to withstand the aerodynamic forces of 400-mile-per-hour flight. The two halves were then bonded together along the center line, creating a one-piece fuselage without a single rivet or metal fastener. It was cabinet making elevated to aerospace engineering, traditional joinery techniques meeting the demands of modern warfare. A 60-year-old piano maker from Acton, interviewed decades later for an Imperial War Museum oral history project, described the experience with quiet pride. He had built Steinway concert grands before the war, instruments where a 16th of an inch misalignment could ruin the sound quality, where the marriage between precision and artistry determined whether a piano sang or merely played notes. Building Mosquito fuselages demanded the same exactitude, the same attention to wood grain direction, ensuring strength along stress lines, the same careful measurement of adhesive application. Too little and joints would fail under combat loads, too much and excess weight would compromise performance. The same understanding that wood was a living material, responding to humidity and temperature, requiring craftsmen who could read its properties by touch and sight. These men weren't soldiers, but their handiwork would save pilots' lives through sheer quality of construction, through joints that held at 10,000 feet when cannon shells tore through aluminum aircraft like paper, through structures that could absorb battle damage and still bring crews home. The production advantages became apparent immediately. Mosquito fuselage halves emerged from their molds in half the time required to rivet together a comparable metal bomber fuselage. No waiting for rivet holes to be drilled and deburred. No need for the specialized presses that shaped aluminum sheets. No welding sparks. No metal filings, no industrial processes that required years of training to master. Just glue, wood, pressure, and patience. By spring 1941, the Salisbury Hall workshops were producing fuselage sections 40% faster than conventional metal construction methods. More importantly, this approach was scalable. Every furniture factory in Britain, every carpentry shop, every workshop with skilled woodworkers could potentially manufacture Mosquito components without competing for the aluminum and steel that Spitfires and tanks demanded. De Havilland had found a way to expand Britain's aircraft production capacity without straining the resources that every other military program desperately needed. November 25, 1940. Hatfield Aerodrome, Hertfordshire. Prototype W4050 sat on the tarmac, its yellow training paint bright against gray English skies. Geoffrey de Havilland Jr., the designer's son, settled into the pilot's seat. At 27, he was already one of Britain's most experienced test pilots, a man who had flown dozens of experimental aircraft through their first dangerous moments of flight. But this was different. This was his father's gamble made tangible. 13,500 pounds of plywood and hope, waiting to prove whether wood could compete with metal in modern air combat. The twin Merlin engines roared to life. De Havilland Jr. advanced the throttles. The Mosquito accelerated down the runway, light and responsive, and lifted into the air with an ease that surprised even its test pilot. For the next 40 minutes, he put the prototype through basic handling tests, climbs and turns, and dives, feeling how it responded to control inputs, noting any vibrations or structural concerns. When he landed and climbed out of the cockpit, his report to the assembled engineers and Air Ministry observers was succinct and professional. "She handles like a fighter." The numbers from that first flight validated de Havilland's calculations. Empty weight: 13,500 pounds, 4,000 pounds lighter than comparable twin-engine metal bombers. Top speed in initial tests: 388 miles per hour. Not quite the promised 400, but close enough to silence the loudest skeptics. Fast enough to outrun most German fighters, quick enough to suggest that the final optimized version might reach even higher velocities. The wooden fuselage showed no signs of structural stress. The bonded joints held perfectly. The lightweight construction translated directly into performance advantages that metal aircraft couldn't match. For the first time since de Havilland had unrolled his blueprints at the Air Ministry, the impossible started looking merely improbable. But the Air Ministry remained unconvinced by test flights over peaceful Hertfordshire. They wanted combat trials. They wanted proof that this wooden wonder could survive not just controlled experiments, but the chaotic violence of real war, where Messerschmitts hunted bombers through hostile skies and anti-aircraft shells filled the air with lethal fragments of steel. May 1942. The first operational Mosquito squadrons received their aircraft with a mixture of curiosity and skepticism. These were crews who had survived tours on Wellingtons and Hamptons, men who understood that defensive gun turrets and armor plating were what separated the living from the dead over Germany. Now they were being handed bombers with no guns at all, aircraft built from the same material as their kitchen tables and told that speed alone would keep them alive. Squadron leader Gordon Slade, 26 years old, had flown 2 full tours on Wellington bombers with 149 Squadron. Of the 10 crewmates he had trained with in 1940, 7 were dead, shot down over the Ruhr or the North Sea, victims of night fighters or flak batteries that turned the sky into a steel storm. He had watched Wellingtons absorb punishment that should have destroyed them. Aluminum skin shredded by cannon shells, tail sections barely attached, hydraulic systems leaking, and still they limped home because metal could take damage that organic materials could not. The idea of flying over Germany in a wooden aircraft, unarmed and relying entirely on speed, felt like trading armor for a prayer. His first mission briefing changed nothing about those doubts. A daylight reconnaissance run over Wilhelmshaven, photographing naval facilities in broad daylight, the kind of mission that would have been suicidal for conventional bombers. Mosquitoes would go in alone. No fighter escort, no formation for mutual protection, just 2 men in a wooden aircraft betting everything on the promise that Luftwaffe fighters could not catch them. Slade and his navigator, Flight Lieutenant James Harper, climbed into their Mosquito on a clear morning in June 1942. The cockpit was cramped compared to the Wellington, no separate stations for gunners or bomb aimers, just pilot and navigator side by side in a glazed nose section that offered visibility in every direction, but also meant they would see exactly what was coming to kill them. The twin Merlins started with a sound Slade recognized from Spitfires, that distinctive growl of 12 cylinders producing over 1,000 horsepower each, engines built for fighters now pushing a bomber to fighter speeds. They lifted off from their base in Cambridgeshire and climbed east toward the North Sea. Crossing the enemy coast at 28,000 feet, Slade pushed the throttles forward and watched the airspeed indicator climb past 350 miles per hour, faster than he had ever flown in combat, faster than seemed possible for an aircraft carrying cameras and fuel for a round trip to Germany. Below, the Dutch coastline slipped past, then the green farmland of occupied Holland, then the industrial haze of the German naval ports. Harper worked the cameras, calling out landmarks, adjusting settings, doing the job they came for while Slade scanned the sky for the fighters he knew would come. They appeared 8 minutes into German airspace, two Messerschmitt 109s climbing from below, their pilots spotting the lone British bomber and moving to intercept with the confidence of predators who had done this hundreds of times before. Slade watched them close, judging angles and distances with the precision of a man who had survived by understanding exactly how much time he had before guns opened fire. The Messerschmitts climbed hard, engines straining, closing to within 800 yards. Then something happened that Slade had never witnessed in 2 years of combat flying. The German fighters began falling behind. Not slowly, not gradually losing ground in a stern chase that might take minutes to resolve, but immediately and obviously unable to match the Mosquito's sustained speed at altitude. Slade maintained 370 miles per hour, straight and level, while the 109s behind him gave everything their Daimler-Benz engines could produce and still watched the gap widen. After 90 seconds, the German pilots broke off, turning back toward their base, acknowledging a reality that went against everything the war had taught about bomber vulnerability. For the first time in his combat career, Slade flew over Germany feeling like the hunter rather than the prey. The cameras finished their work. The Mosquito turned for home. No shots fired, no damage taken, no desperate evasive maneuvers or emergency descents. Just speed, exactly as de Havilland had promised, proving sufficient where armor and guns were not. The mission logs from the following months told a story that transformed skepticism into demand. Between September 1942 and March 1943, Mosquito squadrons flew 1,500 sorties over occupied Europe, photo reconnaissance missions deep into Germany, mapping factory complexes and naval installations, high-speed courier runs carrying critical intelligence, precision bombing raids on targets too small or too well defended for heavy bomber formations. The loss rate across those 1,500 missions was 0.6%. 9 aircraft lost compared to the 4.8% loss rate that Lancaster heavy bombers suffered during the same period flying at night with full defensive armament. The mathematics that had made Bomber Command's casualty rates unsustainable in 1940 were inverting. Mosquito crews had better odds of completing a tour than any other bomber squadron in the RAF. Word spread through the training pipeline. Pilots requested Mosquito assignments. Navigators volunteered for squadrons converting to the wooden bomber. The aircraft that looked like a furniture maker's fever dream was becoming the most sought-after posting in Bomber Command. December 6, 1942. A Mosquito B Mark 16s reached 437 miles per hour in level flight during factory testing at Hatfield, faster than any operational Luftwaffe fighter except the late-model Focke-Wulf 190D, which wouldn't enter service for another year. Faster than most fighters Britain or Germany fielded. A bomber outrunning fighters was no longer theoretical calculation, but demonstrated fact, proven in wind tunnels and combat missions and speed trials that erased any remaining doubt about whether wood could compete with metal in modern warfare. The Air Ministry, which had reluctantly authorized a handful of prototypes 2 years earlier, now ordered 1,000 additional Mosquitoes, a production run that would require furniture factories across Britain to transform into aircraft manufacturers, that would employ 40,000 craftsmen in building the wooden wonder, that would prove de Havilland's Gamble had become the war's most versatile combat aircraft. September 25, 1942. 4 Mosquitoes struck the Gestapo headquarters in Oslo in broad daylight, a precision raid that required flying at rooftop level through a Norwegian fjord, releasing bombs with split-second timing and escaping before German fighters could respond. 1 aircraft was lost to ground fire, but the mission succeeded, destroying Gestapo files and killing officers who had been organizing the deportation of Norwegian resistance members. British newspapers carried the story on front pages, a demonstration of capability that conventional bombers could never execute, proof that speed and precision could achieve what mass formations could not. Churchill called it a masterpiece of courage. What it really was vindication. The Air Ministry ordered more Mosquitoes. Production scaled from dozens per month to hundreds, and just as confidence in the wooden bomber reached its peak, disaster emerged not from enemy action but from the material that made the Mosquito possible. Late 1943, Mosquito production had scaled to 300 aircraft per month, distributed across multiple factories from Hatfield to Leavesden to plants in Canada and Australia. What had begun as a carefully controlled manufacturing process in a requisitioned country manner was now an industrial operation spanning 2 continents, employing thousands of furniture makers and carpenters who had transitioned from peacetime craftsmanship to wartime production. The pressure to deliver aircraft faster to meet Bomber Command's insatiable demand for the wooden wonder inevitably compromised the precision that had made early Mosquitoes so successful. Quality control inspectors at assembly plants reported inconsistencies in wood moisture content, variations in adhesive application, deviations from the exacting standards that de Havilland's original team had maintained when production numbered dozens rather than hundreds. The warnings were noted, logged, and largely ignored in the urgent push to get more aircraft into combat squadrons. Then Mosquitoes began falling out of tropical skies. The first crash happened in Burma, a Mosquito on reconnaissance patrol over Japanese-held territory that simply disintegrated at altitude, wings separating from the fuselage, the aircraft tumbling earthward in pieces while the crew had no time even to attempt escape. Accident investigators recovered wreckage from the jungle and found something that turned skepticism about wooden aircraft into immediate crisis. The glue joints had failed. Not from combat damage, not from structural overload, but from moisture infiltration that caused the casein-based adhesive to delaminate, to lose its bond strength, to turn supposedly solid structures into layered sheets of wood that came apart under aerodynamic stress. A second Mosquito crashed in India within a week. Same failure mode, wing spar separation traced to adhesive breakdown. Then a third in Ceylon, killing 4 more airmen, bringing the death toll to 17 men in crashes that had nothing to do with enemy action and everything to do with the fundamental material choice that made the Mosquito possible. The critics who had opposed wooden construction from the beginning resurfaced with renewed conviction. Wood was unsuitable for combat aircraft. The tropical deployments proved it. Britain had gambled on furniture maker technology and now pilots were paying the price. November 1943. 174 Mosquitoes in Southeast Asia, India, and the Middle East were grounded pending emergency structural inspections. Squadrons that had relied on the wooden bomber for reconnaissance and strike missions suddenly had no aircraft. Crews who had survived dozens of combat sorties over Germany now faced the possibility that their own aircraft might kill them before the enemy ever got a chance. The grounding order spread to other theaters as investigators tried to determine whether the problem was limited to tropical humidity or represented a systemic flaw in Mosquito construction. De Havilland received the reports at his office in Hatfield, reading failure analysis documents that described exactly how moisture had penetrated improperly sealed fuselage joints, how the casein glue absorbed water and lost cohesion, how production scale-up had introduced quality variations that weren't apparent until aircraft spent weeks in monsoon conditions. He was 61 years old now, his son still flying Mosquitoes in combat, and every structural failure felt like personal culpability, like he had sent young men into battle with aircraft built to furniture standards rather than combat requirements. The investigation teams worked through December, inspecting every grounded aircraft, measuring moisture content in wood samples, testing adhesive bond strength under various environmental conditions. What they found was damning in its specificity. When Mosquitoes were built at Salisbury Hall in small numbers, fuselage molds were carefully ventilated during the curing process, allowing moisture to escape as the glue dried. Wood components were stored in climate-controlled facilities, kept below 12% moisture content, the threshold above which casein adhesive began losing reliability. But as production scaled and shifted to factories optimized for speed rather than precision, those protocols had degraded. Ventilation in molds was insufficient. Wood storage was inadequate. Quality inspections that should have caught moisture problems were skipped to meet delivery schedules. 22% of inspected airframes showed moisture content exceeding safe limits. The problem wasn't inherent to wooden construction, it was a failure of industrial process control, a predictable consequence of scaling artisan methods to mass production without maintaining the standards that made those methods work. At the furniture factories in Hatfield and across Britain, the men who had built these aircraft worked double shifts through Christmas 1943, resealing every delivered Mosquito, retrofitting inspection panels that allowed maintenance crews to check glue joints, applying new protective coatings to prevent moisture infiltration. A carpenter interviewed decades later for an oral history project remembered the weight of responsibility in those weeks. They had taken pride in their work, in bringing aircraft construction skills from peacetime trades, in proving that furniture makers could contribute to winning the war. Now they felt like they had sent young men into combat with furniture that fell apart, with craftsmanship that killed rather than protected. The knowledge haunted them, drove them to work 18-hour days, ensuring that every aircraft leaving the factory met standards that should never have been compromised, that the shortcuts taken in the rush to produce more. Mosquitoes would never happen again. The engineering solution came from de Havilland's materials team working with chemists at the Royal Aircraft Establishment. Casein-based adhesive derived from milk protein had been chosen because it was readily available and produced strong bonds in temperate climates. But its vulnerability to moisture was a known limitation, acceptable when production was small and aircraft operated primarily over Europe, catastrophic when hundreds of Mosquitoes deployed to tropical war zones. The replacement was Aerolite 306, a synthetic resin-based adhesive that maintained bond strength regardless of humidity, that didn't absorb water, that could withstand temperature extremes from Arctic to equatorial without degrading. Retrofitting began in December 1943. Every grounded Mosquito was inspected. Questionable joints were resealed with the new adhesive. Structural tests verified that retrofitted aircraft met or exceeded original strength specifications. By February 1944, all aircraft were recertified for combat operations, the technical crisis resolved through engineering discipline and industrial determination. But trust, once broken, took longer to rebuild than airframes. Pilots who had watched colleagues die in structural failures didn't forget that the aircraft supposed to be safest in Bomber Command had killed through construction flaws rather than enemy action. Air Ministry officials who had reluctantly endorsed wooden construction now questioned whether the entire Mosquito program should be canceled, whether future orders should shift back to conventional metal bombers, whether de Havilland's gamble had ultimately failed despite early successes. The Wooden Wonder's reputation hung by threads as thin as the glue joints that had failed over Burma. Then in January 1944, an opportunity emerged to prove the Mosquito's worth in the most audacious precision strike of the entire war, a mission that would require everything the aircraft could do and nothing that it could not. February 18, 1944. Amiens, occupied France. Inside the stone walls of a 19th-century prison, 700 French resistance members waited in cells for interrogation, torture, or execution. The Gestapo had been methodical in their arrests through the winter of 1943, rolling up networks across northern France, capturing radio operators and saboteurs and organizers who had coordinated intelligence gathering and railway demolitions that disrupted German military logistics. Among the prisoners were key figures whose knowledge of resistance operations threatened the entire underground structure across Normandy and Picardy. Scheduled for execution the following morning were 12 men whose interrogations had revealed enough information to compromise dozens of other cells. London received urgent messages through surviving networks. The prisoners had to be freed, or the resistance in northern France would be crippled precisely when Allied invasion. Plans needed maximum local support. A ground rescue was impossible. German troops garrisoned throughout Amiens would respond within minutes to any commando raid. The only option was an airstrike so precise it would breach the prison walls without killing the prisoners inside, so fast that German fighters would have no time to intercept, so daring that only one aircraft in the Allied inventory could execute it. The Mosquito. Operation Jericho required capabilities that defined why the wooden bomber existed. The Amiens prison sat in a residential neighborhood surrounded by civilian homes and a hospital. Heavy bombers dropping 1,000-pound bombs from altitude would destroy the prison and everything around it, killing prisoners and French civilians in roughly equal numbers. Fighter bombers lacked the range to reach Amiens from England with enough fuel for combat and return. What the mission needed was an aircraft that could carry bombs precisely to a small target, fly at rooftop level to avoid radar detection, navigate by visual landmarks through occupied France, and outrun any German fighters that scrambled to intercept. Group Captain Percy Pickard, 32 years old, commanding officer of 140 Wing, received the mission briefing on February 16th. He had flown bombers since 1940. Survived more combat missions than most crews completed in 2 tours, earned the Distinguished Service Order and Distinguished Flying Cross for actions over Germany. He understood exactly how difficult Operation Jericho would be and exactly why Mosquitoes were the only aircraft that could attempt it. 19 Mosquitoes from 3 squadrons assembled at RAF Hunsdon on the morning of February 18th. The strike force was divided into 3 waves. The first wave, led by Pickard, would target the prison's outer walls, blowing breaches through which prisoners could escape. The second wave would strike the guard barracks and administrative buildings, killing or suppressing German personnel who would otherwise shoot fleeing prisoners. The third wave would remain overhead, ready to bomb additional targets or provide cover if German fighters appeared. Each Mosquito carried 4 500-pound bombs with delayed fuses. Enough explosive power to demolish concrete and stone, but requiring precision placement to avoid killing the people they were trying to save. The weather briefing was marginal. Low clouds over the Channel, snow forecast over northern France. Visibility poor but acceptable for pilots navigating by landmarks rather than instruments. Pickard gathered his crews for final instructions. The mission profile was dangerous in ways that had nothing to do with enemy fighters. They would fly to France at wave-top height, 50 feet above the Channel to avoid German radar, then navigate inland using church steeples and road junctions and railway lines as reference points, staying low enough that ground observers would have no time to alert defenses. The final approach to Amiens prison would be flown at 280 miles per hour, barely above stall speed for a Mosquito, slow enough to aim precisely, but fast enough that anti-aircraft gunners would have seconds at most to track and fire. The formation crossed the English coast at noon, dropping to minimum altitude over gray winter water, 19 wooden bombers painted in camouflage patterns, carrying a mission that combined desperation and precision in equal measure. They reached the French coast near Le Tréport, climbed slightly to clear the chalk cliffs, then descended again to treetop level, racing inland across snow-covered fields. German troops on the ground saw British bombers flash past before they could reach for weapons, RAF roundels visible for an instant then gone, the formation navigating by Pickard's map reading and dead reckoning, every church and crossroads matching pre-mission reconnaissance photographs. 14 minutes from the coast, the distinctive walls of Amiens prison appeared ahead, exactly where they should be, exactly as intelligence photographs showed them. Pickard's Mosquito climbed to 800 feet, enough altitude to dive toward the target, enough height to give his bombardier a clean angle of attack. Behind him, the other aircraft in the first wave followed, spacing themselves for sequential bombing runs that would concentrate explosives on the outer wall without wasting ordnance on already breached sections. Pickard dove toward the prison wall, throttling back to bombing speed, the Mosquito stable and responsive even at the edge of its performance envelope, exactly the handling characteristics that made precision strikes possible. His bombardier called ranges, adjusting aim point, compensating for wind drift. Bombs away. 4 500-pound bombs fell toward gray stone walls that had held prisoners for over a century. The Mosquito pulled up hard, climbing away from the target as explosions ripped through the outer wall, blasting a gap 20 feet wide through masonry 2 feet thick. The second Mosquito bombed, widening the breach. The third struck another section of wall. Within 90 seconds, the first wave had blown 3 separate holes in the prison perimeter, each large enough for men to run through, each positioned to give prisoners multiple escape routes. The second wave came in lower, targeting the guard barracks with the same precision, bombs detonating in administrative buildings where German officers coordinated prison security, collapsing structures and buying critical minutes before any organized response could form. Pickard's Mosquito made a second pass, assessing damage, confirming that the breaches were adequate for mass escape. That second pass put him in range of German anti-aircraft guns that had finally oriented on the attacking aircraft. Flak bursts walked across the sky, black puffs of exploding shells throwing shrapnel through the air where mosquitoes flew. Pickard's aircraft took hits in the two. Port engine and fuselage, fragments punching through plywood skin, severing control cables, starting fires in systems that kept the wooden bomber flying. He maintained control for 3 miles, getting clear of Amiens, putting distance between his dying aircraft and the mission area. Then the Mosquito rolled inverted and dove into frozen fields, disintegrating on impact, killing Pickard and his navigator instantly. The mission succeeded. 258 prisoners escaped through the blasted walls, including key resistance leaders scheduled for execution the next morning. 2 Mosquitoes lost, 10% casualty rate, high by Mosquito standards, but acceptable for a target this dangerous and a mission this critical. Churchill received reports that evening, reading accounts of precision bombing that conventional aircraft could never execute, of wooden bombers flying at rooftop level through occupied France to free men whose knowledge was vital to invasion plans taking shape for Normandy 4 months away. He called Operation Jericho a masterpiece of precision and courage, but what it really demonstrated was that de Havilland's impossible idea had become an irreplaceable weapon. That speed and wood and furniture maker craftsmanship had created capabilities no metal bomber possessed.